In this example, we're going to calculate the matrix exponential e to the at if the matrix A is given by 2, 1, 1, 2. So just a quick reminder about what a matrix exponential actually is defined as. So e to the at, where A in this case is a matrix, is given essentially by its Taylor expansion equivalent, which is the matrix I, the identity matrix, plus A times T, plus A squared T squared over 2 factorial, plus A cubed T cubed over 3 factorial, plus, and on and on and on. So essentially you have an infinite series here where you have increasing powers of this matrix A. So how do we go about actually solving this? Well, we rewrite this as just the infinite sum k equals 0 to infinity of a to the k, t to the k over k factorial. And then what we remember is that the Cayley-Hamilton Theorem tells us that because this is a 2 by 2 matrix, we can actually write this as, actually we can write, Cayley-Hamilton says that we can write the kth power of this matrix A is actually given by some coefficient, which depends on k, times the imaginary matrix, plus some other coefficient, say C1, which depends on k, times A. So because this is a 2 by 2 matrix, we can write it as a linear combination of powers of A, which is 1 less than the size of A, which is 1 in this case. So we can rewrite A to the power of any number k here as this expansion here, which now allows us to rewrite the A to the k down here as what we have above. So that's k equals 0 to infinity, t to the k over k factorial, that stays around. But now that we have a to the k like this, we can instead write this as c0, sum c0 of k times I plus c1 of k times a. And what that allows us to do is that actually allows us to rewrite this as I times some infinite series t to the k over k factorial c0 of k plus a times, same thing, sum k equals 0 to infinity t to the k over k factorial times, in this case, c1 of k. So what we have here, all we did was we split this sum here into 2 parts. One part that is multiplying I and one part that is multiplying A. The part that is multiplying I, what we'll call that is B0, and it is a function of t. And we have here the thing that is multiplying here, it is some function B1 of t. Okay, so how do we figure out what these functions actually are? So let me just finish rewriting it like this. B0 of t times I plus B1 of t times A. So what we can do now is to figure out what this function B0 and B1 are. We can actually appeal to the Cayley-Hamilton Theorem, which tells us that essentially, after some work, we realize that e to the lambda t has to satisfy the same equation. It has to be B0 of t times 1. So just rewrite that, B0 of t times 1 plus B1 of t times lambda, where lambda is an eigenvalue of A. Okay, so now what we can do is we can sub in this equation has to be true for any eigenvalue, so we can sub in our 2 eigenvalues from the matrix A once we find them, to make 2 equations and 2 unknowns, the 2 unknowns being B0 of t and B1 of t. And using those 2 equations and 2 unknowns, we can solve for B0 of t and B1 of t, and we can plug them back into here to finally calculate our matrix exponential. So with a little bit of work, the eigenvalues of A are actually equal to 3 and 1. And so now that we know the eigenvalues of A, what we can do is we can use each of these in the above equation here, so that we have e to the t, we're using the eigenvalue of 1, is equal to b0 of t plus b1 of t times 1. And then the other eigenvalue, e to the 3t, is equal to b naught of t plus b1 of t times 3. And that will give us two equations, say equation 1 and equation 2, where now the unknowns are these unknown functions b naught of t and b1 of t. So solving equations 1 and 2, so solving 1 and 2, just by using some elimination here, what we find is that b naught of t is equal to 3 e to the t minus e to the 3t over 2, and b1 of t is equal to e to the 3t minus e to the t over 2. So now we figured out what b naught of t and b1 of t are. Now we can go back up here and use them in this expression here to finally calculate our matrix exponential. So therefore, e to the at, this matrix exponential we're looking for, is equal to b naught of t, which is 3 e to the t minus e to the 3t over 2 times the identity matrix, the 2 by 2 identity matrix, plus b1 of t, which is, we actually know this now, e to the 3t minus e to the t over 2 times our matrix A, which is, let me just double check here, our matrix A is 2, 1, 1, 2. So 2, 1, 1, 2. And once we actually combine all this, what we find is that our matrix exponential is given by 1/2 times e to the t plus e to the 3t, e to the 3t minus e to the t, e to the 3t minus e to the t, and e to the t plus e to the 3t. So just to summarize again, the definition of a matrix exponential is given by this infinite sum here, but using Cayley-Hamilton we know that the powers of our matrix A can actually be rewritten as a finite sum of terms here involving powers of A. Rearranging all of that, what we find is that we can actually get this in terms of two functions, b naught of t and b1 of t, each multiplying the identity matrix and the a to the power of 1 respectively. To get those unknown functions, b naught of t, b1 of t, we again appeal to Cayley-Hamilton, which allow us to use the eigenvalues in the exact same equation. And using the eigenvalues in the exact same equation, we're able to solve for b naught of t and b1 of t. And once we have those, we just use them again in our expression here, and we just put everything together, and we achieve the matrix exponential given here.